All right, so we're looking in this one for the x values where the tangent line is horizontal. As soon as you see tangent, you're hopefully thinking then derivative, because remember the derivative tells us the slope of the tangent line. So first thing I would do is figure out what is y prime. So you should have found that it is 4x cubed minus 4x. And that's it, because remember the derivative of 5 is 0, it goes away. Now we need to solve that. We're looking to see where the tangent line is horizontal. Remember that means the slope, in other words our derivative, has to equal 0. Now, in order to solve this, that looks like a factoring problem to me, because it is nicely factorable. So I'm going to factor out that 4x first, which leaves us with x squared minus 1. And then you notice the x squared minus 1, that also factors down even further, so we end up with 0 equals 4x times x plus 1 times x minus 1. Now that it's fully factored, we can go ahead and find our solutions.
No. Wait.
And to find our solutions, we can use the zero product rule here. So I set each of these equal to 0 since they're all multiplied together. And so you should end up finding that x equals, well, 4 times what is 0? 0. That's the one that we tend to overlook. The negative 1 and the 1, we tend to remember those, but remember the 0. So make sure that you remember that piece there.
Wait, 1's a perfect square, right?
Now in this case, are we done?
Yes.
Yes, we are. Because you notice it said find the x values. It didn't say find the points, find the coordinates. We don't need to find the y values, so we are done there.
We were right there. Wait, Mr. Martin.
Now, for today's work, we're going to be continuing with the idea of the tangents and the slopes and all that kind of stuff. But we're specifically going to be doing it here with respect to writing equations of lines. And not only are we going to do tangent lines, we're also going to be dealing with normal lines today as well. So start please by adding this into your notes so you have that definition of a normal line. And then we'll go from there. So normal can often be used as another word for perpendicular. That's the connection why we call this a normal line. So basically, the normal line is just like the tangent line, except that it's perpendicular to the tangent line. So you can kind of see that in that diagram. Now, do you remember how the slope of a perpendicular line compares to the original? If not, you might want to add a little detail into your notes here. The slopes of perpendicular lines are opposite reciprocals. Remember, opposite means flip the signs. So like positive becomes negative or negative becomes positive. Reciprocal means flip the fraction. So we're going to practice that idea with this equation to start with. We're going to write the equation of the normal line to this curve at the point 1, 0. So go ahead and write down the problem first, and then we'll start going through it together. All right, so the first step is that if we're going to know the slope of the normal line, we have to find the slope of the tangent line. That means derivative, right? So step 1, let's figure out what y prime equals here. So remember, we can go term by term. What's the derivative of x?
1 over x. 1.
Just 1.
What? Dude.
Now, what's the derivative of the square root of x?
Plus.
Well, you might have it memorized by now, but if not, let's
1
check
over
here.
X squared.
So x to the 1/2, that becomes 1/2 x to the negative 1/2.
Oh God. 1/2.
And so then that becomes 1 over 2 root x.
That's what I meant.
So that is 1 over 2 root x there. All right, now
Wait, would it be
that's the general equation for the slope of the tangent line. I need to know what the slope is specifically at this point, at 1, 0. So I'm going to plug that 1 in for x. Notice I don't need to plug the 0 in because my equation here takes x in and gives the slope out. It doesn't need the y because it's already built for that. So to find my slope then, I'm going to go ahead and call it m because it's going to be my slope. I'm going to do 1 minus 1 over 2 times the square root of 1.
So that's just 1.
Okay, so then that's 1 over 2. So that's just 1/2. 1 minus 1/2 is
So half.
Just a half. Now that's the slope, remember, of the tangent line. And remembering always what you just found is going to be critical in this process. Because that's the slope of the tangent line. But then what's the slope of the normal line? Well, it has to be opposite reciprocal, right? So opposite means I make it negative because it was positive. Basically flip the sign. If it was negative, I would have made it positive there. So, and then reciprocal means flip the fraction. So 1 over 2 becomes 2 over 1. Of course, 2 over 1 just equals 2. And so the slope of my normal line is negative 2.
That's just the slope.
Now, notice we are supposed to write the whole equation though. So I know the slope of a line, and I know the point that it goes through. We can now then write the equation of the line. So remember old y equals mx plus b?
Yep. Y equals mx.
The most common way people do this, at least, is they'll plug in for y, m, and x. So we'll do 0 equals, because y is 0 at this point, m, negative 2, times x, which is 1, plus b. And then we can solve that. So that gives me negative 2 plus b. I can add 2 to both sides, so 2 equals b. Meaning then that my final equation of my normal line will be y equals negative 2x plus 2. And that's it. Now a little side note here. I did the equation of the line by plugging it into y equals mx plus b. Some of you might do that actually by using point slope form, where you do y minus y1 equals m times x minus x1.
No.
If that's your method, go with it. It's a good method. So we find our derivative, we plug our x value from our point into that derivative. That's what we're doing down here. And we end up finding that the derivative at negative 1 equals 7. Now, remember what that means. That means that the slope of our tangent line equals 7. Now that's just the slope of the tangent line. Now I will need that, but of course it's not the only thing I need. I also need to know the slope of the normal line. To find the slope of the normal line, remember it is the opposite reciprocal. So opposite, flip the sign. Reciprocal, flip the fraction. And so then we have both slopes. Now use both of those slopes with the same original point to find your equations of the lines. So you'll notice here, for our tangent line, we get y equals 7x plus 8. For our normal line, y equals negative 1/7 x plus 6/7. Yeah, we got to deal with the fraction. Sometimes it happens. Deal with it. So we're shifting gears a little bit here. So we took a look at finding the equations of normal and tangent lines. I now want to take a look at a little bit of detail about the whole motion equations thing, position equations, or otherwise known as displacement equations. And that's the sort of thing we're looking at here. In this case, it's a height equation. That's a type of measuring displacement here. So the vertical face of El Capitan in Yosemite National Park is about 3,000 feet tall. I like using it as an example because it's conveniently a neat number. A stone that falls from the peak would then have that equation, h of t equals 3,000 minus 16t squared. So, if you take a look at this equation here, and I actually plug some number in for t. what are the units for h? In other words, what is h measured in here? Yeah.
Feet.
Yeah, exactly. H would be the feet. Okay? So then, what about h prime of t? In other words, the derivative of h of t. What would that be measured in?
-32.
Well, a great way to think about it, remember that d over dx kind of notation? This would be like dh over dt, right? So it's how h is changing over how t is changing. Well, height is measured in feet. We just saw that. And t is measured in
Time.
it's time. Now, it doesn't say here what it's measured in. So we're going to have a little bit of assumed knowledge here. If you haven't seen these types before, these types of equations, if it doesn't say otherwise, go ahead and assume it's in seconds. In this case, it is. And so it would be feet per second. Okay. Now, if it's feet per second, then what does that actually represent? What's it mean? Yeah, that's how fast it's going. It's like speed or velocity. Yep. Okay. So then what about h double prime of t? Our second derivative. Well, that would be like the change in h prime over the change in t. So h prime, remember, that was feet per second.
Over.
And then that's over the change in t. Again, t, another second, so that's another per
it is acceleration.
second.
It was acceleration.
So yes, as some of you are remembering from physics right now,
Every second it goes up.
that is acceleration.
Miguel, you know that one.
And so this sometimes can be a little bit tricky for people to get their head around, though. What this means is that every second, the speed of the object changes by some amount per second. So in other words, the velocity is changing over here every second.
I was mentioning.
One other thing I do want to mention, though, because the notation can be a little bit weird, feet per second as a unit, it can also be written as feet per second squared.
Oh, that should make
So when you see feet per second squared, that's what it really means. It means feet per second per second.
Now that looks like.
So then add this information into your notes. It'll help you keep straight how these displacement derivatives work, where s of t is representing the initial position, and then you can see how the derivatives work from there. If you took physics, there should be a lot of echoes with what you've seen in physics as well here. Now, as you note, like I'll use this last line as an example, notice the notation. So if I want to write an equation for acceleration, that is a of t, I could do that by finding the derivative of velocity, or I could do that by finding the second derivative of position. So that's what that notation is telling us there. All right, so now, another problem kind of like that first one, a little bit different though. So take a moment, read through the problem here so that you know what we're kind of dealing with. And if you're curious, yes, I actually went and found out how tall it really was in order to be able to write the equation and come up with this stuff. So,
Why is it leading?
I appreciate that.
the first question here is, what is the height of the tower? We actually can know this just by looking at the equation.
56.
And for those of you who have taken physics, it's going to be easier, but everybody can know. So what is the height of the tower in this problem?
56.7.
It is 56.7, and our units in this case are meters. Yeah, so it would be 56.7 meters. Now, how do we know that? Well, if you took physics, you might just be used to the structure of these types of equations. But if you didn't, you could always think about, well, if it was dropped, that means that the height is how tall it was when it was first dropped. In other words, when t was 0, how high was it? And you can see there, if I plug 0 in for t, I get 56.7. All right, next up. Does the acceleration due to gravity change over time. Now this is very much a physics question, right? And yet you can actually use what we've learned here to answer it. Because how do I write an equation for acceleration?
Oh, it's just the double prime.
Yeah,
Double.
double prime. It's the second derivative. So take a moment, please. Find out what is the second derivative of this equation. So we find h double prime of t, and you should have found that it was negative 9.8. So going back to our question that we're answering here, does acceleration due to gravity change over time?
No.
Is there a t in this equation? No.
It's a constant.
It's constant. It is always negative 9.8. No matter how long it's been falling, gravity is always pulling it at negative 9.8 meters per second squared. Which, of course, is true. The force of gravity is always constant. It's not changing and fluctuating over time.
Everything falls in the same time.
One last piece here for your notes. We've been using derivative for a few different things here. We use derivative to find the slope of the tangent line. We use derivative to find instantaneous velocity of if we start with position. All of these different uses for derivative can all be described as a rate of change. And so that's a big idea I need you to get down. Anytime you see something that is a rate of change, derivative is involved in some way.